Hey, thanks for joining us in this first NMR video. I believe it's chapter 10, but in this video we just want to kind of go over more of the theoretical background about the NMR spectroscopy, so that in the next couple of videos when we talk about sort of the more practical things, it'll make sense to you. Okay. Alright, so NMR spectroscopy, that's done in a NMR instrument that looks something like this. Usually if you walk up to and look at it, the more impressive part is the magnet, the big magnet, which often has a superconducting magnet in it, which means it needs to be cooled to like almost absolute zero type of temperature. And so there's a ton of liquid helium, liquid nitrogen to cool that, so it's pretty big. That's the impressive part. The expensive part actually is the big computer next door that processes all the signals. Inside the magnetic coil, right, like you drop the sample. I say drop, but it's floating with the air, so that it's not like just dropped into it. There's a flow of air here, and then there's a sample. I think you will do an NMR lab eventually, and with that sample, you get some signal that looks something like this. And if once you sort of learn the ins and outs of NMR, you would be able to even figure out structure of an unknown compound as complex as something like this structure here. Okay, so that's kind of the goal. Well, we're not going to in this class maybe be analyzing something as complex as this structure, but we're going to be analyzing some compounds. And then in our class, you will try to, you will not just try, but you're going to be able to elucidate the structure of a completely unknown molecule by figuring out the relationship between each atom, which is really exciting. There's something it's so small you cannot see, but you can figure out what it looks like, right? Earlier we talked about IR spectroscopy. The NMR depends on the radio wave, much weaker strength and much longer wavelength electromagnetic radiation. Is the radio wave. It's literally the same wavelength that like radio signals are transmitted over. Okay, and so that's the NMR here. This is NMR. Okay, and it's much weaker energy that's transmitted, but it's enough to. It's not enough for electrons to do something or cause different vibration of the molecule, kind of like we saw with IR. In Gen Chem, you might have talked about UV vis absorption, right? But it's not quite as strong as that. But so it doesn't do anything to the electrons. It does something to the spin state of the nuclear particles like protons, and because each subatomic particle is always spinning. And when it's spinning, right, and it's charged, like it has its own current, electrical current essentially, and so it creates its own magnetic field. So if you apply a really strong external magnetic field, right, it's gonna those two are going to interact, and that's kind of the idea. And then you could flip it to the higher energy spinning direction or higher energy spin state, and then when it relaxes you can get some signal from that. That's the idea. So the visual picture you could have in your mind is if you have a big strong magnet applied to the sample. Remember that picture of the NMR instrument from a couple of slides ago, right? The spin state or spin direction of the subnuclear particle like proton, which that's the main thing we're going to be looking at, so I'm just going to say proton. The spin direction of the proton, each proton in each atom, is going to be just in a random direction, right? But normally, because they're not told to line up in any direction, but once you apply this really strong external magnetic field, they will sort of twist to like line up with the external magnetic field direction. A lot of them are going to line up in the same direction as the external field, but sort of kind of by chance, like some will line up in the exact opposite direction. And you might think that's kind of counterintuitive, right? That some, it's intuitive that most of them are going to be in this lower energy alpha spin state, which just means it's in the same direction as the external field. Some will be in the beta spin state, which is the opposite direction. That might be counterintuitive. It's the picture you could have in your mind, without getting into really deep physics here, is like fish in the river, right? Like, did you notice that, like, if when you apply water current to a school of fish, right? Like, they usually line up with the direction of the flow of the water. Most of them actually line up in the exact same opposite direction of the flow. So that's kind of like the beta spin state. Some might be still swimming in the same direction as the flow, which would be the alpha spin state. So without getting into too deep of a physics lecture here, that's kind of the explanation of alpha and beta spin state. Now, when you apply that, like we said, before you apply an external magnetic field that's coming from that big magnet in the NMR, right, the directions are random. But once you apply it, they're going to line up either into the alpha state, same as the external, or the opposite, exact opposite of the external, which is the beta spin state. Now, the idea is that there's a tiny bit of energy difference between these two states. It's not huge, but enough that energy difference can be overcome by irradiating the exact radio frequency of photons, that's the electromagnetic radiation, that's equivalent to this energy difference, right? That is called resonance. Like, this proton resonates with that radiation or radio frequency, so that it can get promoted to the higher energy beta state, right? And that's the spin flip. Okay, and once it gets promoted to the higher energy state, it can eventually relax back down to the normal spin state. So that this is kind of the normal statistical distribution. Like, there's always some that are in the weird beta spin state. It's kind of like big population, right? Like, there's some of us, most of us kind of behave in a expected way, and then some of us behave in a little different way. That's just kind of how it is with nature, right? It just goes back to that statistical distribution. And when it does, it releases some radio frequency, and that's what we can observe as a NMR signal. Okay, so that's what that is. And again, kind of going over the same thing again, but with just kind of a hypothetical number. If you have what's called 300 megahertz NMR, that's about kind of slightly low. Well, it's pretty high end. The low end of a high end NMR is about 300 megahertz. So these days it could go as high as 1000 megahertz. That refers to like how strong of a magnet you've got. And we'll talk about like why that might be important later. But 300 megahertz is kind of an average, okay, or around the mill instrument. And with that external field strength, a proton would absorb at, you don't need to know this number, but 70,459 Gauss of magnetic field strength, if it's completely naked, as in nothing shielding it. But as you know, even hydrogen protons, right, like those are surrounded by at least 2 valence electrons normally, right, at least formally speaking. So because there's some electrons around that proton, that the electrons also have sort of their own, they can create their own magnetic field because they're a current that's spinning and moving. And so for that reason, they can block the effect of the external magnetic field, if that makes sense, right? The electron cloud could block that. So it doesn't absorb anymore at this field strength. What needs to happen is the field strength has to be a little bit higher, just a little bit. It doesn't take much to overcome that blockage by electrons or shielding by electrons. So you need to apply a little higher field than the proton absorbs the photon or radio frequency, and it can flip to the beta spin state, right? And so what does that tell us? What that tells us is just with a really tiny shift in magnetic field, you could tell, right, like how strong of a radio frequency that each proton had to absorb to flip the spin state. And that in turn is dependent on the electron shielding effect, which in turn is like proportional to how much electron density you've got, right? So what does that tell us? Well, that tells us about each proton, each hydrogen, how much electron density they have. And that's very useful because depending on what functional groups you have or what kind of bond it has, right, there would be very different amount of electron density for each hydrogen. So when the hydrogen is attached to not very electronegative element like carbon, right, these guys are fairly shielded, so it can absorb at a higher field. It would have to absorb at a higher field. Now, if it's very deshielded because it's attached to a very electronegative atom, then it would be it can absorb at a lower magnetic field. And so one of the main things we're observing in NMR spectrum, NMR spectroscopy, is how shielded each proton is. Okay, hope that makes sense. And from how being able to observe how shielded some proton is, we could tell what kind of functional group or bond it's a part of. Okay. Here's an example of a NMR spectrum, and this is of a very simple compound, benzene. It may be surprising to you at first that it would only show one peak in the NMR, proton NMR. Why is that? Well, it's mainly because of the symmetry. Does it make sense that no matter how you rotate this, like any 6 ways, right, like the structure is really the same? And so each of these protons is said to be equivalent, and so for that reason you only see one peak. Another thing you can observe is what we would call chemical shift, which is this x-axis in an NMR spectrum. That depends on what radio frequency absorbance this particular proton has to absorb to do the spin flip. That divided by the magnetic frequency. And the reason is this frequency is actually described mathematically like this, which I don't need you to know or memorize that, but I just need you to know that it depends on the external magnetic field, which depends on the exact magnet and its strength of that magnet, right? So that's not great, because depending on which magnet you're using, depending on which NMR instrument you're using, this value is going to be different, and that means, right, like you can't compare the numbers between different labs that study these compounds. So that's not great. So what we do to normalize everything across all magnets so we can compare the numbers is we divide that number by the magnetic frequency, which is essentially how strong of a magnet you have of your instrument. And so if you look at the units, this is in hertz. This is typically in million hertz or megahertz. So that becomes parts per million. So the unit for chemical shift is given in parts per million. And so you can expect the same exact chemical shift for the same compound on any magnet. This peak was also there in the last spectrum where I didn't discuss it, TMS reference peak. That stands for tetramethylsilane. These chemical shifts are kind of somewhat relative though, and so for that reason we want to have internal standard or some sort of standard that sets the exact 0 ppm. So to set the lower field, right, it's nice to this is a high field area where like proton is very much shielded. To set that reference, it's nice to have something that's as shielded as possible, and that would be tetramethylsilane, which is very electron rich. It's these methyl groups attached to a sort of a metalloid element, which is electron rich, because they like to donate their electrons, not take. And so that is by definition set as 0 ppm is the chemical shift of tetramethylsilane, and everything else is in reference to that. So this is very much deshielded, so it's downfield. Or technically low field, and then this is this means it's very deshielded compared to TMS, and this is this is fairly shielded, this proton, for the reasons we'll discuss. It's higher up in chemical shift, like 3 ppm. The sort of the lingo is towards the 0 area, we would call that the upfield. The higher numbers, we call those downfield. And one of the things I want you to sort of master is to be able to use chemical shift range tables like this. Each types of protons is depicted here, depending on different functional groups you have. The orange ones are kind of variable, so you can't say too much based on the exact chemical shift. Notice those are all protons on a hetero atom. those are not very reliable. But these hydrogens on a carbon, you notice these are all hydrogens on a carbon, the blue ones, those are very reliable, fairly defined ranges. So you could do a lot to diagnose what type of functional groups you have based on the chemical shift. Now, there's of course some overlap, right? And that's when you have to use other information like what molecular formula do you have? Do you have oxygen in it? Do you have nitrogen in it? You could even consult IR spectra to see what kind of functional groups you have and so forth. Now, just to kind of give you an example, right, like benzene, it looks like this because of its interesting resonance, right? This tells us that these pi electrons can like go run around in a circle like forever. I don't know if you ever wondered like if you could trap electricity in like a loop of wire, maybe you'll have forever electrical current and a forever power. Well, that actually happens in benzene ring, right? These electrons are forever moving around in a circle. And so for that reason, they do create some magnetic field, and that adds to the external field, which means they get, from the proton's perspective, they feel like they're already in a very strong, extra strong external magnetic field because of this extra magnetic field that's the pi electron current is creating, right? It's like a ring current of pi electrons. So they would feel de-shielded, right? Because the external field is essentially stronger for those protons. And remember that if the chemical shift is given like this, if you have to apply like higher frequency of radio wave to for it to do the spin flip, right? That's gonna be in the de-shielded part of the NMR spectrum. So it's gonna be downfield, and much downfield. It's around 7.2 to 3 ppm. And alkenes, the pi current is not as extensive as benzene in a ring, in a circle, forever kind of a current. So for that reason, these protons are de-shielded for the same reasons as benzene, but not as much. So it's usually around 5. And this could vary from like 4.5 to like almost 6, depending on what else is attached to this alkenes. That's one of the things we'll talk about is chemical shift. The shift in chemical shift is often additive. Like if you have so many things that would de-shield it, those effects are kind of additive. Okay, so being part of alkene shifts you to 5, and if being next to oxygen shifts you by another 1 ppm, then it's going to show up around 6 ppm and so forth. Now, alkyne, which is kind of like alkene, but that the magnetic field direction is very different for alkyne because of the extensive pi system. There's 2 pi bonds, right? So for that reason, they kind of have more of a shielding effect, and so for that reason, it's not as de-shielded. It's fairly high field, like upfield, I should say, around 2 ppm and so forth. Okay. Now, the other thing about NMR is you could tell a lot from the number of signals, okay, number of peaks you see. This spectrum sees 2 of them. Sometimes you see these tiny peaks. They're often like impurities, or this tiny peak at 7.26 ppm. That's actually the tiny bit of proton present with the deuterated solvent you're using. It's a deuterated chloroform, meaning all the hydrogens are replaced with deuterium so that it's NMR invisible. You don't see the signal, but in the process, there's always a tiny bit of proton, regular hydrogen impurity instead of deuterium. So that's what you see here. But anyway, you see just this one peak for these. Oh no, I can't go back with this PowerPoint. Sorry. You see one peak. Once you saw one peak for those 3 hydrogens on a methyl group, because those 3 hydrogens can rotate around the single bond, right? So that makes those 3 totally equivalent. Now, technically, 2 hydrogens on a cyclohexane, they're not equivalent because they're in a very different environment when they're in axial as opposed to equatorial positions. However, remember the chair flip, right? As long as the chair flip can happen pretty rapidly, like non-substituted cyclohexane, there's nothing that keeps it in one chair conformation over the other. Now, it'd be a different story if there's like a T-butyl group here, then it's locked into that one stable chair conformation, then it will be different. But when there's a rapid chair flip, these two can essentially be equivalent within that NMR time, acquisition time. So often you just see this average of the two, if that makes sense. So for that reason, in these molecules that we highlighted all the equivalent protons as the same color, like these three, all 6 of ethane are equivalent. So if you take NMR of that, you only see one peak because of the symmetry and the single bond rotation. Because of the symmetry, these two methylene protons are equivalent, but these two, because there's no chair flip with the cyclobutane, orange protons are different than these green, which is different than this methine CH proton, right? And then I'll let you figure out this situation. These three and these three are equivalent because of the symmetry in the middle. Okay, so just kind of as a practice though, see if you can identify all the equivalent protons in these molecules. And what I might do with you right now is I'm going to go over this molecule during class. Maybe we'll practice on this molecule together. Now, this molecule, hope it makes sense that these 3 protons here on this methyl are equivalent, so that's one signal. There's one proton here, so that's second signal. And then this methyl is different than these other methyl groups, so that's third signal. Now, this methylene, CH2, is a little tricky because you have a chiral center here. The proton on this side of the screen and the back of the screen, those 2 protons are in a little different environment. The proton on this side is on the same side as this methyl. The proton in the back is in the same side as the proton at this chiral center. So those 2 are said to be diastereotopic. They're in diastereomeric type of environments. They're in 2 different environments, and so for that reason, you're going to get 2 different signals here. Now, that effect is not as much felt at this far away methyl group, so that would be 1 signal. So to summarize, we should expect 1, 2, 3, 4, 5, 6 signals for this molecule because of the diastereotopic effect. Okay. So just to summarize NMR, the number of signals tells you how many different kinds of protons you've got. The location on the spectrum tells you how shielded of a proton you have. That tells you a lot about the functional group. And one thing we didn't talk about, we'll talk about more later, is the area of the signal tells you a lot about how many numbers of protons of that particular type, that particular kind, you do have. Like, remember we saw that CH3, 3 protons were under the same one signal, but the area or how big of a peak you've got tells you how many protons you've got under that peak, if that makes sense. And one thing we haven't talked about, there's going to be splitting of each signal based on the neighboring protons. That tells you how many neighbors you have, which is going to be really helpful. But just to wrap this up, NMR is applied in medicine a lot, it's not called NMR in medicine. We often call that magnetic resonance imaging, but it's actually the exact same instrument as an NMR that we use in chemistry. And the reason why this is useful is because you could look at the inside of a body without being invasive, and it's even safer than X-ray. Well, as long as you're not like a cyborg with metal parts or something that gets attracted to magnets, right? Because X-ray also comes with its own risk of like radiation risks. But what the MRI does is, remember that when nuclei get irradiated with radio frequency, which that's the reason why it's safe, is the strength of the electromagnetic radiation you're using is the same as radio frequency, which is the same as like radio or Wi-Fi or Bluetooth. Those are in the radio frequency range. Okay? So as safe as those might be, it's as safe as MRI is. And when you apply that and you go from beta, you go to the beta spin state and relax back down to alpha spin state, depending on the proton's environment, they have a different length of time for that relaxation to take place, and that's called the T1 relaxation value. And that is different depending on which tissue you're talking about in the body, because it's different compounds. Okay, and so that's why we could do whole body NMR, which, by the way, we do have an MRI instrument in our building. It's not meant for humans though. It's meant for like small samples, or even like a mouse, tiny small animals. So we could do MRI to do things like what kind of different tissues are found in a particular solid sample. Like in the medical MRI, that's big. The solid sample is humans. Like, so you could see that there's like a liquid in the spinal cord where it shouldn't be and stuff like that. Or you could plan the surgical line of attack, plan how to do the surgery on the brain. All of that is possible with the NMR or MRI technology. So sorry for the long video, but here's it, well, MR background for you.